Hello everyone, presenting to you Signals and Systems J Component by Ashutosh Pandey 16 BC 0203, Devansh Dutt 16 BC 0279, Tanmay Pathak 16 BC 0336, Aditya Raj 16 BC 0386. As advised by our faculty Loknath M, we have prepared a MATLAB code on power spectrum from autocorrelation. We will start our slides with detailed explanation of concepts behind the code. We'll be starting off with explanation of concepts behind the code. So let's begin. Importance of MATLAB in signals and systems. Commands of MATLAB are organized by topics in signals and systems. Each of these commands has a number of options that extend its usefulness. For example, polynomials. Polynomials arise frequently in systems theory. MATLAB represents polynomials as row vectors of polynomial coefficients. For example, the polynomial s square plus 4s minus 5 is represented in MATLAB by the polynomial p equal to bracket of 1, 4, minus 5. The following is a list of the more important commands for manipulating Following are some commands on the screen. Now we'll start off with Laplace and Z transforms. Laplace transforms are an important tool for analysis of continuous time dynamic systems, and Z transforms are an important tool for analysis of discrete time dynamic systems. Important commands to manipulate these transforms are included in the following list. For instance, residue, one sim, step, impulse, PZ map, residues, and many more. A number of these commands work with several specifications of the LTI system. One such specification is in terms of the transfer function for which SYS is replaced with TF numerator denominator, where num and den are the vectors of coefficients of the numerator and denominator polynomials of the system function. Frequency responses. There are several commands helpful for calculating and plotting frequency response given the system function for continuous or discrete time systems as ratios of polynomials. For instance, Bode n of t. Plot the Bode diagram for a continuous time system whose system function is a ratio of polynomials n of s divided by d of s. Freq s n, d. Compute the frequency response for a continuous time system with system function n of s divided by d of s. Fric z n of d. Compute the frequency response for a discrete time system with system function n of z divided by d of z. Fourier transforms and filtering. There is a rich collection of commands related to filtering. A few basic commands are listed here. FFT of x. Compute the discrete Fourier transform of the vector x. FFT of x. Compute the inverse discrete Fourier transform of vector x. FFT shift. Shifts the FFT output from the discrete range frequency range 0 to 2 pi to minus pi to pi radians. Filter NDX. Filters the vector x with a filter whose system function is n of z divided by d of z, includes some output delay. Filt NDX. Same as filter except without the output delay. In addition, there are a number of filter design functions including furls, furl1, furl2, inverse frequency Z, Ramis and Butter. There are a number of windowing functions including Boxcar, Hanning, Hamming, Bartlett, Blackman, Kaiser and Chebwin. A quick summary. Let's summarize what we have done here, partly as a guide what we would like to do next. There's so much involved, all of importance, that it's hard to avoid saying everything at once. Realize that it will take some time before everything is in place. The Fourier transform of the signal f of t is f of s integration minus infinity to infinity f of t e to the power minus 2 pi ist dt. This is a complex valued function of s. One value is easy to compute and worth pointing out, namely for s equal to 0 we have f of 0 integration minus infinity to infinity f of t dt. In calculus terms, this is the area under the graph of ft. If ft is real, as it most often is, then f of 0 is real even though other names of the Fourier transform may be complex. The domain of the Fourier transform is the set of real numbers. One says that f is defined on the frequency domain and that the original signal f of t is defined on the time domain or the spatial domain depending on the context. For a non-periodic signal defined on the whole real line, we generally do not have a discrete set of frequencies, as in the periodic case, but rather a continuum of frequencies. The set of all frequencies is the spectrum of f of t. Not all frequencies need agger. F of s might be 0 for some values of s. Furthermore, it might be that there aren't any frequencies outside of a certain range. That is, f of s equal to 0 for mod of s large. These are called band limited signals and they are an important special class of signals. They come up in sampling theory. The inverse Fourier transform is defined by g of t integration minus infinity to infinity e to the power 2 pi ist g of s ds. Taken together, the Fourier transform and its inverse provide a way of passing between two equivalent representation of signal via the Fourier inversion theorem. We note one consequence of Fourier inversion, that f of 0 equal to z integration minus infinity to infinity fs ds. There is no quick calculus interpretation of this result. The right hand side is an integral of a complex valued function, and result is real. A periodic function does have a Fourier transform, but it's a sum of delta functions. We'll have to do that too, and it will take some effort. Chapter 2, Fourier transform. Now remember that f of s is a transformed complex valued function, and while it may be equivalent to f of t, it has very different properties. Is it really true that when f of s exists, we can just plug into the formula for the inverse Fourier transform, which is also an improper integral that looks same as the forward transform except for the minus sign? And really get back to ft. Really? That's worth wondering about. The square magnitude modulus of f of s square is called the power spectrum, especially in connection with its use in communications, or the spectral power density, especially in connection with its use in optics, or the energy spectrum, especially in every other connection. An important relation between the energy of the signal in the time domain and the energy spectrum in the frequency domain is given by Parseval's identity for Fourier transforms, which is integration minus infinity to infinity mod of ft whole square dt. This is also a future attraction. Now here comes the most important topic, correlation. Correlation is a measure of similarity between two signals. The general formula for correlation is integration minus infinity to infinity x of t into x of t minus tau dt. There are two types of correlation: autocorrelation and cross correlation. Autocorrelation function. It is defined as correlation of a signal with itself. Autocorrelation function is a measure of similarity between signal and its time delayed version. It is represented by R of tau. Consider a signal x of t. The autocorrelation function of x of t with its time delayed version is given by R of tau equal to integration minus infinity to infinity x of t into x of t minus tau dt for positive shift, and integration minus infinity to infinity x of t into x of t plus tau for negative shift, where tau is searching or scanning or delay parameter. If the signal is complex, then autocorrelation is given by R of tau equal to integration minus infinity to infinity x of t into x of t minus tau for positive shift, and minus infinity to infinity x of t plus tau into xt for negative shift. Now let's take a look over properties of autocorrelation function of energy signal. Autocorrelation exhibits conjugate symmetry, that is R of tau equal to R of conjugate minus tau. Autocorrelation function of energy signal at origin, that is tau equal to 0, is equal to total energy of that signal, which is given as integration minus infinity to infinity modulus of x of t whole square dt. Autocorrelation function is maximum at tau equal to 0. Autocorrelation function and energy spectral densities are Fourier transform. Autocorrelation function of power signals. The autocorrelation function of periodic power signal with period t is given by the formula given. Properties: autocorrelation of power signal exhibits conjugate symmetry. Autocorrelation function of power signal at tau equal to 0, that is at origin, is equal to total power of that signal. Autocorrelation function of power signal is maximum at tau equal to 0. Autocorrelation function and power spectral densities are Fourier transform pairs. Now let's have a look at density spectrum. Let us see density spectrums. Energy density spectrum. Energy density spectrum can be calculated using the formula listed, that is minus infinity to infinity integration mod of x of f into 2tf. Power density spectrum. Power density spectrum can be calculated with the formula listed below. Introduction of main project. The power spectrum of a time series describes the distribution of power into frequency components of composing that signal. According to Fourier analysis, any physical signal can be decomposed into a number of discrete frequencies, or a spectrum of frequencies over a continuous range. The statistical average of a certain signal or sort of signal as analyzed in terms of its frequency content is called its spectrum. Methodology. To compute power spectral density estimate of a signal, we can use any of the two approaches. Compute the FFT of the signal and square its amplitude, or the other way around, compute the biased autocorrelation function and take the FFT. Computing by autocorrelation method. We take the function which is in front of you on the screen. So guys, we have finally arrived to our MATLAB code, the intricacies of which have been already explained in detail. I suggest you to pause the video and clearly analyze each and every line of the code. These are the output graphs, which clearly shows the autocorrelation of the function. This graph depicts the output power spectral density. Thanks a lot for being with us.